This is part 2 of section 4.1. We need to talk about this number we call E. E is approximately equal to 2.71828. This is a number that in a lot of ways is like pi. It comes up very naturally in a whole lot of different situations, and it is a number that never ends and never repeats. So we are stuck using approximations for these all the time. Now, your calculators will have an E button on there, and they are in several different places, okay? On this calculator, you can see that we have E blank here, and you have 10 blank here. If I want to do E to some power, I would hit this. And then if I hit it twice, that's going to make the 10 to the exponent come up. But I really want E to something, and then I would type in the number here. If you ever need E, just plain E, figure E to the first power, because every calculator requires an exponent on your E. So that's how you would enter it on this one. On this calculator, the E button shares a space with this LN. And there's a reason for that that will become more clear in later sections. But for this one, you would have to hit second and then that button to get the E to a power to come up. And then if I wanted the first power, I would type that in. All right, one more. For these graphing calculators, your E button is right here. It's also sharing with the LN, which it makes complete sense once you learn what LN is. So to do that, to enter that, you would have to hit second and then that E to the X button. And again, you would get the exponent. If I type in 1, I'll get the approximation. Okay, so let's use our calculators to approximate each of these values. So if I want to approximate, and we're supposed to go to 3 decimal places, I want to approximate E to the negative 0.95. So E to the negative 0.95 is approximately 0.38. That's a 7, so this becomes a 7. So this is approximately 0.387. Okay, let's do E to the 3.4. E to the 3.4 is approximately 29.96. That's a 1, so that stays a 4. Okay, and let's approximate E to the negative 0.75, except I typed it in wrong, 75, and I get 0.472. Okay, you need to be comfortable using your calculators. What we are about to do, you want to keep the numbers in your calculators as long as possible, because we're about to do some problems and there are going to be a lot of intermediate steps where you may be tempted to write down an approximation and then use that, but you'll end up causing bigger errors. So you really want to learn how to use your calculators. Okay, so let's look at a real-world application of this stuff. Compound interest. Okay. I actually used this information one time when I was buying my first car alone. I was doing the financing part, and the guy was trying to not be very honest with it, and I happened to have a graphing calculator in my purse. I pulled it out, dropped it on the desk, and said, I teach this stuff. Would you care to recalculate? That was fun. Anyway, all right, so formulas for compound interest. So if you have your interest in an investment and it compounds n times per year, and basically what that is saying is, like say it's compounded every month, then it takes your balance and it figures out a certain percent of interest and then adds it to your bank account. And then the next month, the interest you get is you're going to be getting interest on your previous interest. Okay? So in general, the more times per year that your interest is being compounded, the better off you are. Okay, and it's given by this formula. We'll talk a lot about this in a second. And there is a limit on the amount it can do. So if it says continuous compounding, then basically this is compounding more than every minute, more than every second, more than every nanosecond. It is all of the time, and it has a different formula. Okay. A is the accumulated value, so the amount of money you have. P is the principal, and the principal is how much money is invested initially. These are always investments. If you're putting this in a savings account, then you are investing in the bank. If you take out a loan, then the bank is investing in you. So it is always an investment. It just depends on which side of it you're on. Okay? So however much money is invested, this is how much you would get overall. The rate is the percentage of interest, and we write it as a decimal always. N is the number of times it's compounded per year. And T is the time in years. It's very important that you keep it as a decimal. It is very important that you keep it in years. Okay, so what we're going to do is we have a general investment, and we're going to talk about it as, you know, what happens based on the number of times it's compounded. We want to find the accumulated value of an investment of $5,000 for 10 years at an interest rate of 6.5% if the money is compounded, and then our end values are going to change here. Let's just talk about what's going to be the same every time. The accumulated value is what we're looking for. $5,000 is the principal. Our time is 10 years. And the interest, or the rate, is 0.65% as a decimal. So this is 0.065. Okay, so what I'm going to do just to make my life a little bit easier is I'm going to rewrite this one with this information in it, and then on each of these problems that require this formula, I'm just going to have to plug in my n. So this would be A is equal to 5,000 times 1 plus 0.065 over n, and that n is going to change every time, raised to the nt, so 10n. Okay. So let's say that we have this investment, and it is going to be compounded semi-annually. This means 2 times per year. Okay, so this means in this case our n value is 2. So I'm going to come up to this, and I'm going to plug in n equal 2. And this is what I need to calculate. Now you can do this in pieces, or you can put it all in your calculator at once. I think that it tends to be a little bit easier if you just go ahead and calculate this exponent and not try to enter it like this. So that's 20. That's usually just a tiny little calculation right there. Now let's talk about entering this in our calculators. All right. You want to make sure that you're using your parentheses correctly. So 5,000 times 1 plus, we have our fraction button, which is right here on this calculator, and nearby on the others. So I would do 0.065 over 2. Make sure you get out of that fraction, do your parentheses, your exponent button, and you can enter 10 times 2 here, or you can just enter 20. And we get this. 9,479 and a decimal. Now we're always, because this is money, we're going to round to 2 decimal places. That's just sort of a given. So this amount is approximately $9,479, and that's going to be 19 cents. Okay? So if you make this investment and it's being compounded twice a year, this is how much money you're going to have at the end of 10 years. Okay, so now let's do the same thing, but quarterly. In this case, it's going to be 4 times per year. Okay. In general, the more times you compound per year, the larger this value should be. Okay, so now we're doing basically the same thing, except right here and right here we're going to have a 4. So this amount that we end up with is 5,000 times 1 plus 0.065 over 4 raised to the 10 times 4. So right here, that's going to be a 40. So enter this in the calculator again. So 5,000 times 1 plus 0.065 over 4 raised to the 40th power. And I get 9,527. So $9,527 and what is that going to be, 79 cents? It is larger. Okay, so we expect, more times you compound, the better off you're going to be. All right, so let's do the same thing but monthly. In this case, it's going to be 12 times per year. So that means where this 4 is, where this 2 was, we're now going to plug in and equal to 12. So this is 5,000 times 1 plus 0.065 over 12 to the 10 times 12. So right here, I'm going to put in 120. So 5,000 times 1 plus 0.065 over 12, close parentheses, raised to the 120th power, and you get 9,560 $9,560, and that's going to be 92 cents. Okay, so it is increasing every time, but honestly what happens is the more times you do it per year, it still increases every time, but it slows down as to how much it's increasing. So if I do semi-annually, I get a lot, but if I do it quarterly, I get a bit more. Monthly, I get a little bit more. And if I did weekly, it would be a little bit more. Daily, hourly, minutely, secondly, nanosecondly. It's going to keep increasing, but it's not going to increase very much the further along I go. And the natural question is there a limit? What happens if we did it every single time? So let's look at it if it's compounded continuously. Now, there's no number to plug in for n here because continuously is more than every nanosecond. Okay, it is all the time, as many times as you can possibly imagine. Okay, and there is a limit to this. If you see the word continuously, you do not use this formula. You will only use this formula. A is equal to P e to the RT. A lot of people read this as PERT. Okay? The principal times E, and that's the number E, raised to the rate times the time. Okay, so if I'm using A equals P e to the RT, our principal was 5,000. E raised to the, our rate was 0.065, and the time was 10 years. Okay, now I'm going to enter this in my calculator again, 5,000 times E, whoa, wrong button, E to raise to the 0.065 times 10, and that should do it. So our amount is approximately $9,577, and that's going to be 70 cents. Now this value is larger than this value, but it's still fairly close. I mean, from here to here versus here to here, this jumped up, what, about a little over 30, and here you jumped up 17. It's going to keep slowing down as you go up, but it will continue to go up, but this is our upper limit. It will never be better than this.